Okay, good morning, everybody. Yeah. Well, it's a real pleasure to welcome you to the University of Lleida to participate in this international workshop that starts today and will finish next Friday. Now we have here in the table Dr. Jorge Mateu, and the floor is yours.
Yeah, thank you very much, Vice Chancellor or Vice Rector or Provost. Yes, Martin. I think the first word that I really would like to tell you is thank you for being here. I'm sure that after 2 years, I mean, remember that this is the 10th edition of METMA, 20 years of METMA. Talking informally, just a few minutes ago, I said that in my first METMA, 20 years ago, I had more hair on my head than right now. So this is a consequence of time flying over these 20 years. The thing is that we are here. It was kind of unexpected, right? That we should have met 2 years ago, and then COVID came, and then we all stayed at home. And finally, in this year, we started to reconstruct this METMA workshop, and here we are. So my very first words is really thank you to all of you and to those that are listening to us online. Thank you for being here. Thank you for taking your luggage, taking your plane, taking your train, and being here. And I'm saying this especially for those coming from abroad, from really abroad and really long distances to here. So thank you by heart. I think if you are here is because you know what is METMA about. And METMA is about distinct. small group of people working in very kind of similar things in terms of spatial statistics. And this is the big thing here. I mean, there are no parallel sessions. Everyone will be here in this room, listening all together to the same speaker, and clearly sharing experiences in terms of research that we all work individually. And this is the good point with METMA. I'm sure that all of us have attended and are attending many other conferences that are big ones, and then you just go to a subset of the different seminars. But here, we all be here. We all be listening to the same one. We all be sharing our ideas. So this is, for me, the big thing with METMA. Small group of people working in similar things, similar ideas, similar research works. But there is another thing. The thing is that I remember when this METMA started, again, 20 years ago, that was around 2000, 2002 exactly. The thing is that most of us, we didn't, at that moment, we didn't meet each other at that moment, especially at the Spanish version, because METMA, the very first edition, was a Spanish version, and I don't know if you know that METMA is an acronym in Spanish. But clearly, I mean, we had that success in that first edition that we said, okay, that's fine, now everything should be international, everything should be in English, and let's invite everywhere in the world. That was the second edition, right? But the first edition was in Spanish, and with this acronym that is in Spanish. And those who really want to know what is METMA about, in terms of the meaning of the acronym, just let me know, and I will tell you, but that's in Spanish. But what I'm saying is that at that moment in time, we were kind of, each of us didn't know each other, right? So that was a moment where, okay, that's fine, let's meet together, let's chat together, and let's try to set a common path in the next years. And those next years have passed, here we are, and now we know, basically we know each other, every one of us know most of the rest of the people here in the room. And this is the great thing here, right? So this is one thing. Another point is that, and some of the people have approached me and said, Jorge, is it true that this will be the very last METMA? And I said, the very last? Well, it depends on you. It depends on people knowing to get the idea of organizing the next METMA here in Europe. But what is true, what is certainly true, is that I have in mind, we have already started to work on this idea of organizing what is called a Latin American METMA. That will be a Latin version of, let's call, our European or more international METMA. The reason is that, I don't know how many Latin American students are here, but very few. And the reason is that for them is, there is a big community growing year by year of young people starting to work on spatial statistics. But these people, they have problems, economical problems in coming to Europe. So let's do the other way around. So let's try to organize something there, and let's move there those that we can from here, right? So the idea is to organize something like, I don't know how it will be called, but will be a Latin version of METMA. And what I can announce here, not many details, but what I can announce is that it will probably be in Ecuador. But this is just an idea. It's there, it's in the air, but I really would like to make it real, and so that Latin American METMA, I hope that it will have as success as our more international METMA, right? But it doesn't mean that one will substitute the other. We could have the two of them running in parallel. But I think this is good for Latin American countries, just to help them to keep on moving in this area of spatial statistics. So that is a kind of big announce here, although many people knew, especially those closer to me, because I was talking with them. But I'm really happy to think about in this direction, because that's something that will help them in many senses, right? Good. And now coming back to our let's say program, and not to make this very large. Well, I mean, it's a pleasure having all the keynote speakers on one side, the invited speakers on the other, and then the rest of the people. You know that there will be, this is something we will discuss during these days, there will be 1 or 2 special issues coming from this conference. I mean, there is nothing announced in the webpage at the moment, but we have in mind announcing them during these 2.5 days during the workshop, right? This is just a kind of motivation, especially for young people, yes, to rewrite what they are presenting here in terms of a paper and then submitting the paper to these special issues, right? Well, this is one thing. And second thing is that you know that there will be online. I mean, everything will be on screening process. I think there is a link to YouTube. So clearly, what we every seminar it will be just online. So people from anywhere, they will be listening to us. And in particular, there will be 2 keynote speakers that will be having their session online. It's Marian Scott, which is coming later today, and Noel Cressy. The 2 of them will give their seminar online, so it will be exactly the same thing. The only thing is that rather than having them in person, they will be online. So, but the rest of the people will be online, and they can have on the chat questions, and the chairman of each session will translate these questions into the audience and into the speaker, right? Good. I think there is no more to say except that really have fun. I mean, the idea again is to chat with everyone, to have fun of this, to learn, and to share experience with among all of us, and that's all. I mean, that is, for me, that is the real message out of this: having fun with science. There is one thing, and we are organizing in my university, which is called a pint of science, which is having a beer in a pub, in a bar, but talking about science. So here, we're not having pint out in the room, but in any case, a pint of beer, but in any case, the thing is that you should have fun chatting, talking with people, and talking about science and many other things. Thank you very much for being here, and now I translate the word to Olga.
Okay, thank you very much, Dr. Mateu. And now is the turn of the local chair, Dr. Carles Comas.
Thank you very much. I was in the first METMA. Sorry, it's mobile. I was in the first METMA. I was a PhD student at that moment in Glasgow. And for me, it's really, really a pleasure to be the organizer of the 10th edition of METMA. I still remember, sorry, yeah. For me,
Use the other.
yeah. Yeah. Okay. So I was in the first METMA. I mean, 22 years ago. I was at that moment. No.
You disappear.
Hola. Hola. Sí. Okay. You hear me? Yes? No? Hola? Ah, right. Yeah. Okay. I was saying, I was at the first METMA, 22 years ago. At that moment, I was a PhD student at the University in Glasgow, at the University of Strathclyde. And for me, it's a pleasure to be the organizer, one of the organizers of the 10th edition of this workshop here in Lleida. I still remember the day that we talked with Jorge about this possibility. That was in the year 2018, so that means 4 years ago. And during this time, we have canceled this scientific meeting twice, in 2020 and 2021, because of the pandemic of coronavirus pandemic. And now I'm really glad, because this year, finally, we can have our METMA, our 10th edition of METMA here in Lleida. So as Jorge has said already, we have a wonderful program with excellent talks. So I'm sure that we will enjoy this first-class scientific event here in Lleida. And I hope you enjoy also your visit, your stay here in the city of Lleida. As I have to say again, thank you very much for coming. And welcome to Lleida and to the University of Lleida. Thank you.
Thank you, Dr. Comas. Well, the University of Lleida is really happy to host events like this workshop for two reasons. The first one is that it indicates that we have very well-known and recognized researchers in the field. And the second, because it is a way to open our university, our city, and our region to all attendees. Let me tell you just a little about the university. According to the World University Rankings, the UDL is around the middle of the almost 2,000 universities evaluated. But considering the Young University ranking, is in the position 200 among 800 universities. If we consider the Sustainable Development Goals, in the last ranking, the University of Lleida is in the range between 300 and 400 out of 1,400 universities. In general, that is good, but when we study just a little more in deep specific SDG, we are the 72 among almost 1,000 universities in gender equality, and similar position in reduction of inequalities. That we are, as you can imagine, we are really proud of that. One way to measure the size of one university is the number of students. And University of Lleida has around 11,000 students, including almost 700 PhD candidates who are enrolled in 14 doctoral programs. And considering dates from last year, no, the last before, the UDL has around 700 researchers. Almost a half are women. I think maybe it is not the case in your field, but we are trying to increase the number of women in these disciplines. We obtained 16 million euros from competitive national and international research calls, and within this, 3.6 million euros are from contract with companies and other institutions. In 2020, we published almost 900 articles in SC journals, but within them, 72 are highly cited articles. We have half of our articles in Q1, half of our articles are with other international authors, and half of our papers are in open access. For these reasons, we are in very, very good position within the 7,000 universities evaluated. We rank 1,500 in number of papers. A better position considering the Q papers, and much better, almost 500 in the number of papers led by UDL researchers, who are among the 10% most cited in their field, according to Scopus. I'm sure that UDL researchers working in statistics are contributing very much to these good results. Well, in the workshops that begin today, you will have, as Jorge told, you will have the opportunity of interact with the top scientists in your area who will participate as speakers. Yeah, the old people, we say, are always the invited speaker, but also with other colleagues and PhD candidates. As a result of the interaction and the content of the program, you will start new collaborations and go home with new ideas. Please don't miss the visit to the old cathedral, because you will see something that will be familiar for you, that is in your logo. Of course, enjoy the dinner. And if you were planning to stay for the weekend, I suggest you not to stay in Lleida, in the city, because it's so hot. But go anywhere in the Pyrenees, because you will have a wonderful experience. Okay, have a very, very profitable workshop and enjoy Lleida and this university.
Yeah, so now just 1 minute, and then the first keynote speaker will start. So I was saying that not only Peter, but his group working there in Lancaster, in Chicas, they've been developing all these methods, but with many purposes. But I really would like to highlight one, and that one is trying to improve human lives, people. The thing is that, and that can be done using statistical methods. And this is the big thing here, right? Not only developing methods per se, but developing methods to solve real problems so that they come into society and we can improve many, many aspects of society. And this is the big thing from my really humble point of view of what Peter and his group is doing, they are doing. Having said this, let me introduce and say that Peter will be talking about this design and analysis of prevalence surveys for neglected tropical diseases. A pleasure, Peter, of being here.
Thank you, Jorge and colleagues, and thank you for the invitation. Is the sound okay? Yeah, Bernie. So, yes, we've got the title, we've got the cast, and a couple of these people have moved on and are now working elsewhere, and there are new people taking their place. But it is very much a joint effort from the start. I think I can use this. Yes. Okay, and if you want to follow up anything that's in the talk, then it's essentially all published, and I'd be happy to have emails from anybody who wants to ask me any questions online after the event about following up any of this work. So the first thing to do is to emphasize the title, and this map really says it all. If you think that we're talking about neglected tropical diseases, the clue is in the first word, neglected. These are not diseases like malaria, which, although of profound importance, are also extremely well funded, but these are the diseases that tend to be forgotten in international funding agencies because although they don't kill many people, if any, they do cause an incredible amount of hardship and poor quality of life to the people who are afflicted with them. And we're talking about 1/6 of the world's population, and the map indicates that, of course, this is largely in the tropics, and a lot of the tropical countries featured in this map are also generally very poor countries, and they don't have the resources to deal with the problems that beset them in everyday life. However, help is at hand, and in particular, a nice shout out for the much maligned pharmaceutical industry, because the two diseases that I'm going to be talking about in this talk, onchocerciasis and lymphatic filariasis, can be prevented by routinely administering a pill. Some say once a year, some say once every 6 months. And rather tantalizingly, those pills are donated free of charge by Merck, multinational pharmaceutical company, who make them in a factory in Europe and ship them to the ports of Africa, where the hard work really starts, because the task then is to distribute these pills in very large scale to generally remote rural communities. This program, although notionally it seems to be free of charge, at least at one point in the process, is still very complex, very difficult. It's been running for many years, and of course you do have to keep re-administering the medication if you want to get long-term protection. And so that means that in order to achieve the greatest public benefit, you need to prioritize where to allocate treatment. At any one time in the program, where is the urgency? Where should we be prioritizing treatment? And the clue is in the name where, and this is a conference about spatial statistics, and so that's why spatial statistics is relevant to helping decide where to prioritize action. Okay, so here's the first of the two diseases. There's this rather graphic description from a British explorer in Uganda in 1864. And so you really don't want to get bitten by one of these things. Firstly, because it hurts, but more importantly, that if you're unlucky and the fly was infected with onchocerciasis parasites and nobody does anything about it, then there's a risk that you will be turned blind by early middle age. The statue is in front of the WHO headquarters in Geneva, and it's a very graphic illustration of the consequences of not doing anything about this neglected tropical disease. And this map here looks uncannily like the previous map. Not quite. It's a bit more restricted. But certainly Latin America and Africa are the global areas where this is or has been a public health problem. It's much less of a problem now than it was 50 years ago, not least because of Merck's donation program and the efforts that go alongside that. But it's still a pretty big deal if you're poor in a rural community in any of these affected countries. So, how do we go about finding out where to prioritize treatment? Well, we need to know where the disease is high prevalence, medium prevalence, low prevalence, and so we need to go out into the country and take some samples. And in this map of Liberia, every circle is the location of a rural community where field epidemiologists have gone, they've taken blood samples, they've looked at them under the microscope, and if they detect onchocerciasis parasites, that's a positive, and the circles are color-coded and size-coded into quintiles of the empirical prevalence at each of those locations. The talk is about design and analysis. I won't spend much time on design, although in practice it's of course a very important and time-consuming process in working on design in real life. I don't have a lot to say about the theory of design, but the design questions here are kind of obvious. If you were presented with a blank map of Liberia and your job was to design a survey to look at the variation in prevalence in Liberia, you have to ask questions like, how many places do you need to visit? Where should they be? How many people should you test at each location? And what should you actually use to measure them, right? What's the measurement instrument that you're going to use to estimate prevalence? Because as we shall see later, there are choices. And the choice of which is the best measurement strategy is not always obvious. So let's just look at the where to sample question. And although we're doing spatial statistics, we shouldn't forget the basics. And there's a lot to be said when you're designing a prevalence survey in these situations for randomizing to avoid subjective bias. And there's a lot to be said for stratifying to control for large-scale variation and also for operational convenience, because typically within the country there will be a health geography, and the regional health teams will have their own staff who want to go out within their region and take samples. So stratifying makes sense operationally as well as potentially giving you extra statistical efficiency. But one of the very early findings from spatial statistics, which goes right back, like most things in spatial statistics, to Bertil Matern's PhD thesis, is that actually taking a completely random sample of locations in an area is almost always a very bad idea, right? And I'll show you in the next slide intuitively why that's kind of obvious, but Matern knew it back in the 1950s. And what you really want to do is to constrain your randomization so that you get a good even coverage of the area of interest. It kind of makes sense that if you want to know what's happening countrywide and you believe that what's happening is variable, then you'd better make sure that you've got a representative sample of locations across the country. But one of the things that really critically affects a geospatial prediction is the noise to signal ratio in your data. And the way you get at the noise to signal ratio is that you take measurements very close together, so that you think in terms of spatial correlation, those results should be almost identical. But if there's some noise in the data, then those close pairs of locations will measure the noise, and then that helps you decide on the optimal prediction algorithm. So, and this is really the end of the design part of the talk. Well, not quite, there's one slide to come. On the left, we've taken a completely random sample of locations in a conveniently square country. And on the right, we've sampled in the way that we recommend, which is basically, as point process people will know very well, a realization of what's sometimes called a simple inhibitory process, where you sample at random subject to the constraint that no two of those black dots are within a specified distance of each other. And that turns out, unsurprisingly, I think, to anybody who understands spatial statistics, be a more efficient way of understanding the spatial variation in whatever it is you're measuring at those black locations. Now, that's all very well in a place like this and in a place like Lancaster. It's not always practical in rural Africa. What you have here is a field epidemiologist. And the reason he's on a motorbike is because when he left home a few weeks ago, he was in a Land Rover. And when the roads ran out, he unhitched the motorbike off the back of the Land Rover and he carried on because he'd been given instructions to find communities that he could sample to see what the local prevalence of disease was. And at one point on his journey, he might, for example, encounter, sitting on that path, a lion, as indeed one of them did, and is written up in the records of the field studies, and then thought, well, I'm supposed to go that way, but there's a lion there. I think I'll go that way instead. Now, you try telling that person that they really want a spatially regulated coverage of Liberia, and they will not be very impressed. So as you will see when I show you some data, you don't always get statistically nice designs in this area. And as Alan will tell you on the last day of the conference, you have to be very careful drawing inferences. You have to know why you've got the spatial distribution of points that you've got. Here, I'm going to actually proceed optimistically on the grounds that whether there's a lion on the path or not is probably unrelated to the local prevalence of disease. And so, although we don't have a nice statistical design, I'm going to assume that the reason that these people have sampled some communities and not others is not specifically because of any prior knowledge about the likely prevalence in those respective communities. They're really looking for a countrywide coverage. They don't always achieve it in a statistically optimal way. Right, now the guts of this talk are extraordinarily simple to this audience. If you think about statistics, I don't know in American parlance, but in Britain this might be the sort of thing you would learn in the last year of an undergraduate degree, logistic regression. So in logistic regression you've got the idea that you want to estimate prevalence P, and ever since McCulloch, not McCulloch, he came later, Nolder and Wedderburn did their pioneering work on generalized linear models, the industry standard for this has been a logistic regression model. So in the context that we're working in, where we've got space X and covariates D, which are properties of that space X, here's our logistic regression model. Very simple. What nearly always happens, not just in spatial statistics, but in many other walks of life, is that you find what's called extra binomial variation. And one of a number of ways of dealing with that is to add to the model a random effect. I think if I do that, well, that isn't what I wanted to happen, so never mind, I won't do it. So the only difference between this and the previous slide is that UI on the right-hand side of the equation top right is an unobserved random effect. And you can think of that as a proxy for the things that you would have put into the regression model if you'd measured them. And the classical assumption in so-called generalized linear mixed models is that those random effects are mutually independent. But the first law of spatial statistics is that things aren't usually mutually independent. They're usually correlated. And so finally we have the geostatistical model where we add a second random effect, which is a spatial process which introduces spatial correlation, spatial structure to the problem. But essentially, it's just a logistic regression with some bells and whistles added on. In which context, it's remarkable how long it took for people to start doing this, still. Okay, so what happens if we apply that model to our Liberian data? We get this rather pretty map. We included longitude and latitude as covariates, in particular noticing that at the coast, things are pretty safe in the sense that prevalence is low, and it's in the interior that you tend to get the higher prevalences. We included extra binomial variation at the village level, in other words, to look at non-spatial properties of locations that would affect the prevalence, and the residual spatially correlated variation is that process S of X. Okay. So that if I was forced to, I would say that's my best guess at a prevalence map in Liberia, but it doesn't answer the relevant question. Mainly, but not only, because it doesn't have any estimates of uncertainty associated with it. So what you do is you say, actually, what's the question we're really trying to answer here? So if you take you to the bottom of this slide, in this context, the WHO, for better or for worse, has instructed, or advised rather, African countries to say prioritization for treatment of onchocerciasis should be to areas where local prevalence exceeds 20%. Okay, so the real question is which parts of Liberia have prevalence greater than 20%? And that previous map is of no use whatsoever in answering that question. What we have to do is think of this as a prediction problem in which S is the state of nature, Y is the data that we can bring to bear on understanding the state of nature, T is a specific target for prediction. T is the thing that if we could measure it, would answer our question. Now our model is a model for how the data relate to the state of nature. So we say we need a model for the state of nature S, and we need a model for the data conditional on S. In my context, S is a Gaussian process, and Y conditional on S is a logistic regression. And then prediction just consists of using Bayes' theorem to invert that statement so that we get a conditional distribution of the state of nature given the data, and it follows a fortiori that we have a conditional distribution for any property of S given the data. And the property we're interested in here is prevalence exceeding 20%, yes or no. And as the aforementioned, if only by accident, Peter McCulloch memorably said to me in the pub one evening after a Royal Statistical Society meeting, the answer to a prediction problem is a probability distribution. So this map answers the question. This map is a map of the probability, the predictive probability, that prevalence exceeds 20%. And so I would argue that this map, unlike the previous one, answers the policy relevant question, but critically, it does it with an honest assessment of uncertainty. And in particular, remembering our friend on the motorbike, that tells us where you do need more data. You might have to take a deep breath and decide whether you can afford to get more data, but basically you can say near the coast we know it's low, in the green areas we know it's high relative to the threshold that WHO have advised us, and the pink areas are the don't knows. Okay, I'll come back to onchocerciasis towards the end of the talk, but now I want to talk a little bit about lymphatic filariasis, the consequences of which are rather well explained by the slide on the left. Common name for this disease is elephantiasis. And again, the WHO, after long and sometimes tortuous debate with experts, has come up with a criterion whereby an area can declare to have eliminated this disease as a public health problem if antigene prevalence, in other words, current infection rates, are less than 2%. And that has very serious practical consequences because it means they will no longer get the prophylactic medication, okay? Because somebody else needs it more, basically. And again, these maps all look kind of depressingly similar if you think about the state of the world that we live in. You know? It's the poor people in hot countries that are really suffering from all of these conditions. Okay, so how does the WHO advise people to find out whether an area meets this criterion of having less than 2% prevalence? They do something which some of you may think is less than ideal, which is they say, okay, we'll divide the country into districts, which we call evaluation units, and we'll instruct people to go out into the field. They look up tables provided by the WHO in which they actually, the WHO tables, they look it up and they say, we need 38 villages, and we need 60 children in each village. And if the total number of positive tests is greater than 12, we're in trouble. And they take no cognizance whatsoever of where those 12 positive tests are. And that's it. Whereas the geostatistical approach says, you know what question you're trying to answer, so following McCulloch's dictum, what we can do as statisticians is to the best of our abilities, and in order to use our abilities wisely, we will consult experts on the disease as well. We will come up with a statement of how likely it is that this area has met the WHO criterion or not. And on that basis, somebody has to make the decision on, are they only going to act on certainties, in which case they'll never finish, or are they going to accept a certain margin of error in terms of it being highly likely, high probability, that an area is or is not within this threshold level. So, with help from the team, and in particular Claudia Frontera, who's at the back of the room today, we did a kind of proof of concept using an unusually rich set of data from Ghana, in which the prevalence of lymphatic filariasis had been established through this extensive set of field surveys prior to treatment with the drug. All right? So this is, if you like, the naive or so-called baseline LF prevalence prior to treatment. And you can see there's a lot of spatial variation, and you can see that, as usually is the case in these problems in our experience, that variation is strongly spatially structured. It's not just independent random sampling from a distribution. And basically red is bad news and blue is good news for the people in those areas. So we develop and fit a geostatistical model, and we come up with a predictive baseline prevalence map. and we can turn that baseline prevalence map into a predictive map, which shows that prior to treatment, Ghana had an awful lot of areas that were highly likely, those are the red ones, to be deemed requiring treatment. Okay? So then we said, okay, what does the drug do? What the drug does is it drives down prevalence. So we look at the history of drug administration since those baseline maps were constructed, and in the simplest form of projection towards what we think the country would look like now, we simply shift the log odds. If you look at that equation, L0 x equals Lx minus C, we simply shift on the log odds scale so that the population weighted average of prevalence is at that decision threshold. Why do we do that? Because people in the country, health officials, they may not be statisticians, but they kind of know their communities. And the way things work is that if a country wants to go for elimination, it has to run a survey according to the WHO design at the point at which it thinks it's about ready to do so. If it goes too early, it'll be wasting money, right? And if it goes too late, it'll be missing an opportunity to treat. So it's a decision that they're reasonably sure they'll get right, but it's a decision they have to make on a countrywide basis. WHO will certify, yes, you can go on that basis and do a countrywide survey to see if you meet the elimination criteria. Okay, so with that model, of course, we can simulate what we think Ghana would look like if we did do a prevalence survey now, and of course it's a lot more blue because the effect of the treatment has been to shift the countrywide prevalence down. And we think there would still be some residual dangerous areas, areas where the prevalence is above the 2% threshold. Those are indicated in red, but there's a lot fewer of them than before. Okay, so what we've done is we've evaluated that predictive performance by applying the WHO guideline to the simulated data. In other words, we've simulated a field survey and decisions based on the WHO guideline, also applying geostatistical prediction, and we've compared the results of the two methods. And there are many ways that you could compare them, but the one that seems to us to be most in line with a predictive mentality is to look at empirical positive and negative predictive values. Okay? In other words, we want to know what's the probability, right, that an area that we declare to be safe really is safe. What's the probability that an area that we declare to be dangerous really is dangerous? And we get these ROC curves. Just focus on the top left, okay? So on the y-axis, you've got the positive predicted value, the probability that elimination really has been achieved, given that you've indicated it, right? And on the x-axis, you've got 1 minus the negative predictive value, the probability that elimination has not been achieved, given that you've not indicated it. So where you'd like to be on this graph is in the top left corner, right? And the reason it's a line and not a point is because you have to choose what probability will you say, I'm convinced, right? You can be very skeptical, or you can be take a punt. So you can be anywhere on the probability scale from 0 to 1, and you describe a curve as you do that. The thing that is just a point, the x, that's what happens if you use the WHO guidelines. So basically, what you want to be is as close to the top left corner as possible, and you can see where the WHO guidelines put you. And in the top left, the curve uses the same sampling numbers as the WHO guideline, but applies geostatistical methods to solve the prediction problem. And basically, you can see you do a lot better. What's more encouraging, and initially surprised us in a very pleasant way, is that if you take 1/5 the number of village communities sampled that WHO recommends, you still do better. Not by much, and I would actually say that you do about the same. So in the middle top, you can see that sampling 1/5 as many locations, you get about the same performance as the WHO guideline, if you choose the right value of the threshold probability. And if you really push your luck and go to 1/10 of the locations, you go the other way. Now at the bottom, we do a lot better because the argument, which is probably not strictly true, but it seems there's an element of truth in it, which is that if you're sampling fewer locations, doesn't that mean you can afford to test more people per location? And if you buy that argument, then actually you preserve your superiority over the WHO guideline right through. Now I want to emphasize that this superiority, which is quite marked in this example, is dependent very strongly on the strength of spatial correlation in the underlying process, which won't surprise this audience. but it is not untypical of things that we've found in a range of diseases in a range of countries. So the take-home message is you can save an awful lot of money on your prevalence surveys if you switch to a geostatistical prediction paradigm. And we're currently working with the WHO to write a new guideline which is incorporating geostatistical principles to replace the current one. Okay, now I want to revisit onchocerciasis, and this is a slightly strange story because it turns out that although that pill is very good at preventing you from getting river blindness because it basically kills the parasites, if you are heavily co-infected with another parasite, this little beastie on the left, which is called lower, and you may get a severe reaction to what was generally considered to be a safe drug. And basically that's because this parasite, if you're infected with it, it really multiplies in prodigious numbers. And if you give the pill, it certainly kills the parasites, but then the detritus actually can block up the fine blood vessels. And so in extreme cases, people suffer potentially, in fact, occasionally fatal anaphylactic shock, and they just, within 24 hours of treatment, they die. And that's not good news at all. Now, we're talking about hundreds of deaths compared to millions of treatments, but even so, every death we'd like to avoid. Interestingly, it's before lunch, so I can show you this slide. It's not considered a serious disease. I mean, it looks unpleasant if you've got a worm traveling across the white of your eye, and it makes you ill, but you recover. So it's only a public health problem because it impacts on the safe administration of the drug to control onchocerciasis. So now we've got another prediction problem because we need to know where people are going to actually experience these adverse reactions so that we can either not treat them or preferably treat them, but make sure we've got paramedics on hand to respond promptly if somebody shows signs of an adverse reaction to the drug. And this discovery that people who are heavily co-infected could be at risk of these serious adverse events actually stymied the program for several years. Okay, so the question now becomes, and remember we're always trying to answer a question, and it's never our question, it's somebody else's question. The question now is, where is mass drug administration safe? This generates a whole new set of debates amongst policy experts, entomologists, biologists, public health experts, as to how would you define a safe community. So at this point you play God, you don't worry about statistics. You say, suppose you knew everything about this process. What you would do is say, okay, suppose that Z is the level of infection, which is the number of parasites per milliliter of blood, for a randomly chosen person at X, and W is proportional to the population density as X. Then what you would really like to know is what's the probability that somebody in that community will have more than 20,000, and 20,000 is a number that's not a statistical number, it's a number that's advised by people who've looked down the microscope at these things. They are people at risk, people who have more than 20,000, think about it, parasites per milliliter of blood in their system. And so our goal is to say, well, is that criterion met? And again, you have this unavoidable, to me, decision as to what do you mean by probably? And surprise, surprise, the accepted criterion now is that an area is declared safe if the probability that less than 1% of the population, right, has more than 20,000 parasites per milliliter of blood, if that probability is greater than 0.95. Okay, well, now we're in business. All we have to do is to measure the level of infection of everybody in the community. Now, unsurprisingly, that's difficult. It's expensive. It's actually not just about expensive in money terms. There isn't enough equipment to go around to do it in a timely fashion. So we fall back, well, the current rule of thumb falls back on saying we can't measure people's individual levels of infection, but it is relatively easy to measure prevalence. And so we'll say that, okay, this really is coincidental, we again get this 20% prevalence as the threshold value that people have accepted, saying an area is safe for administration of the drug if the prevalence of parasites in people's blood, lower parasites in people's blood, is less than 20%. Okay, so you need to have high prevalence of onchocerciasis to be prioritized, but you have to have low prevalence of lower for it to be safe for the drug to be administered. And that's not terribly satisfactory. A better solution would be if you could, at least in a sample, measure people's levels of infection. And now you need to model two random variables. You need to model the probability that somebody will be infected, and you need to model the level of infection of that person given that they're infected. So what you can do with some data from Gabon, which has been collected specifically for this purpose, is you can look at the cumulative distributions of MF load, number of parasites per mil, in different communities, about 200 communities Gabon-wide, and you can plot the cumulative distributions, and unsurprisingly, I hope, to a statistician, but certainly unsurprisingly to an epidemiologist, you find that areas with low prevalence, like the red community, also have a short upper tail of the level of infection distribution. Kind of makes sense, doesn't it? That the more disease there is around, the more likely you are to find people who are very highly infected. And it turns out to be true. And so you get this rather nice sheaf of curves, which all have broadly the same shape, but very different intercepts and scale parameters. So what we need is a random effect to capture these two properties, the prevalence and, if you like, the mean, or at least a scale parameter for the distribution of the number of parasites per mil. So this is what we do. We basically write down a probability distribution, which we've chosen to be a viable distribution, and we make its scale parameter lambda a random effect. We have our old friend, the logistic regression, and we make that a random effect. And so now we have a bivariate random effect for each community, and the advantage of this is that if it turns out that those two random effects are strongly correlated, it means that even if you only know one prevalence, you can predict the other. And that's what we do. Because this is, having fitted this model to the data, a plot of the minimum mean square error predictors of the individual random effects. No spatial correlation in this plot. We simply plotted them for each village, and you can see this very strong correlation. So what we then did is we said, okay, well, all we do now, because we're dealing with a spatially varying phenomenon, is we make those random effects Gaussian processes, spatial processes, U of x and V of x. And that's what we did. Now, that means that you can just go into a community and collect prevalence data and predict what proportion of the community will have high levels of infection. That's good, but it's not perfect, because you'd really like to know which members of the community have that high level of infection. And this is where some modern technology really comes to hand, because on the right, you've got something called a lower scope. And what that wonderful device does is you put a finger prick of blood in the well, and you slot your mobile phone in, and the mobile phone takes a movie, and based on the amount of movement that it detects, it estimates the number of parasites per mil of blood. Unsurprisingly, that's A, expensive, and B, there aren't a lot of them around. There might be a couple of hundred of these devices worldwide, and we're talking about treating 100 million people. So if you want to test every individual before you give them the pill, you can forget it. The other recent development from a team in California is a lower antibody test, which detects past or current infection. I'm sure you all recognize the device on the left, but this isn't for COVID, it's for lower. And so we evolved in discussion with our partners in the neglected tropical disease world a strategy saying, wouldn't it be great if we could screen communities with the antibody test, which is quick, cheap, easy, and proceed to the lower scope if the safety is in doubt. And I love that phrase, in doubt, because it really shows that they've got the basic idea that this is a probabilistic problem. And if you're looking for certainty, you better go somewhere else. Right? But if you recognize that this is an inherently uncertain question, you've got to decide what's a reasonable level of doubt on which you're willing to proceed. So we thought, how do we test this two-stage strategy? Well, we do what to us is the obvious thing. We say, well, we haven't just got two random effects now, we've got three. Because if you think of what happens in real time, the first thing that happens is you go in with your antibody test and you estimate the antibody prevalence. Now, if you were to follow that up with the lower scope, you would get a second measure of prevalence, which you hope will be correlated with the first. They're different devices, but there should be some association between them. And the lower scope level, in other words, the number of parasites per mil. And again, what we hope is that what we saw earlier, will translate, and we'll get good correlation. And so we just make the obvious extension of our very simple model that we started with, which is the first of those equations, a logistic regression with a Gaussian process in the linear predictor. We add a second logistic regression which is correlated with the first, and a third log linear model which is correlated with the first two through this sharing of S0 of x, but we add the S1 of x and the S2 of x to the second and third equation, so that if the correlation is weak or even non-existent, the data will tell us that and will not allow us to use the S0 as a predictor for pi and lambda. And we have some covariates here which are often useful in this world. Because we're talking about biting insects, it turns out that if you measure the level of greenness of the local vegetation, which is available as a raster satellite image, and you measure elevation, which is a proxy for suitable breeding conditions for the flies, which is also available as a raster image, those are useful predictors. And that's the latest paper of the ones that I gave you at the beginning of the talk. And so we basically use that trivariate model to test different strategies in this test case in Gabon. So again, the target is the probability that a person chosen at random from one of those communities has a prevalence greater than 20,000 microfilariae per mil, and we can classify each EU as safe or unsafe or don't know. And if it's don't know, that's when we send in the lower scope. Right? So, how does this work? Well, on the left we've got the gold standard. Because we've got lower scope data for every one of those communities, we can actually say what would be the best prediction we could make if we used all of the antibody data and all of the lower scope data, and we get this classification of safe in blue on the left, unsafe in red, and don't know in purple. If we relied on the antibody test, then necessarily you do worse, and in particular you get these don't knows in much greater numbers. There is much more purple in the middle than there is on the left. So basically if you just use the antibody data, then you're left with not knowing quite what to do. But if you then use the two-stage method, in which case, in other words, you only use the lower scope data for the areas that are purple in the middle, then you can see that you recover. In fact, you recover exactly in this case, but that's just a happy accident. You recover on the right essentially the same map as on the left. And the cost and time savings are very substantial, because basically all the things that were blue in the antibody test, you're done. All the things that were red in the antibody test, you're done. And it's only the purples that you have to implement the lower scope on. So that's the end of the story. And I'm very pleased to see that I've got us back on time, because being late for coffee is one of the worst things you can do at a conference. So the message is, it's been a very simple message all through, but it really is very simple. And one of the things that I've found most gratifying in my work in this area is actually getting across very simple statistical principles. And the first one is, there's no need to use ad hoc methods. There's no need to use Bloggs' test for spatial correlation. What you do is you say, what's the question? What's the data? How can I build a model that fits the data and enables me to answer the question? And since the question is nearly always a prediction question, the answer to your question is a predictive probability. And the great thing about working with these guys, in contrast to working with the British government, is that people are willing to tell you what the question is. Now, I don't know what it's like in Spain, but throughout the COVID epidemic, I have never seen a government spokesman stand up and say, if we knew that COVID prevalence was less than X%, we would do the following. Never. That's what these guys are willing to do. They're willing to really think it through and say, yeah, if we really knew that prevalence was such and such, we'd do the following. And if we knew it was such and such else, we'd do the following differently. And that makes it enormously helpful to somebody like me, because you know what you're trying to do. But accepting a probabilistic answer to that, it takes work, right? But once that message has been got through, you're in business. Now, the middle one, if any of you have heard me give any talk before, you've probably heard me use this quote because I love it, which is that we do use statistical modelling to buy information. And that's why the other thing that's been enormously satisfying for me working in this area is the modelling assumptions come as much from the science as from the data, right? This is not algorithmic modelling. This is actually saying, Which covariates would make sense as predictors for the following disease? Why would they make sense? Is it reasonable that they would be linear? I mean, I'm not going into all of those details in this talk, but you can have a genuine dialogue with people who are at the front line, and then you're fairly confident, you still have to do diagnostic checks, of course, but you're fairly confident that rather than just chasing patterns in a morass of covariates, you actually have got the substantively relevant ones. And the other thing which makes the modeling paradigm, I think, eminently justifiable in this context is the scarcity of resources. You don't need fancy statistical models, or arguably any statistical models, if you've got really good, really large, really precise, really accurate data. The data will speak to you loudly. But if the data are only whispering to you because there aren't a lot of them, and there's no money to send the guy on the motorbike out for another round of data collection, then basically the modeling, and in particular these geostatistical methods, really can deliver not just a few percentages, but multiplicative factors worth of gains in efficiency. I spent last week with Claudio designing a nationwide LF study for Guyana, and we ended up recommending that they use 1/3 of the sample size that the WHO guidelines currently recommend, which they were very pleased to hear. So we really put our money where our mouth is, and we'll be analysing those data when they come in later this year. Thank you very much.
Many thanks, Peter. Time for questions, comments? Yes.
It is challenging, and what I would expect, simplicity is relative, isn't it? And what I would expect to be challenged in some audiences is this seems a very simple model, whereas other people would say this seems a very complex model, right? You're right, these things are not as well identified as you would like, but we can find them on this data. Going beyond that level of complexity, no, but yeah, we found serious contributions to alpha 1 and alpha 2. Had we not done so, those maps that I showed you, the 3 maps, would not have looked so different.
Yeah, that's what I'm impressed by, but
yeah.
It seems like you need decent sample size, and you're complaining about not having good enough sample size.
Well, no, bear in mind that when I say a decent sample, I'm talking about hundreds of locations, not thousands, right? You don't need thousands, you need hundreds, right? For the Guyana-wide survey, we've ended up recommending they go to 100 villages. It depends on the spatial correlation, as you know. If when you draw your map it looks like white noise, then you're dead in the water, right? Because you're exploiting the spatial correlation in order to get that gain in efficiency. But certainly for the kind of data sets of the order of a small number of hundreds, that's about as complicated as I would want to push it.
Any other question? Yes.
Thank you. So for your logistic models and also here, so what's the covariance? So the covariance you use, I can see here is vegetation and elevation.
Yeah.
But for vector-borne disease, I found it often also related to weather information. Would that be a useful covariate for?
Potentially, yes. In a way, it comes back to Alan's question, which is that the thing that's most difficult in fitting these models is that sometimes, because we think the likelihood is wonderful, and it is, but it's not intelligent. And if you have both a spatially structured covariate and a latent spatially correlated process, then the likelihood can get confused between them. And it's not obvious to us now, and to be honest, when we started this, we just did it automatically. It's not obvious to us now that the best thing to do is to fit all those things simultaneously. There's an argument for saying you should do the best job you can with a classical logistic regression on covariates, and then hold those covariate effects as offsets to see if there's any residual spatial correlation. And we're sort of switching to that paradigm, more or less, as we speak. Again, but you make a very good point, because it does depend on context. And say for the more we the more we get involved with the country teams rather than working remotely, the more we get that dialogue going. So that for the Guyana study, we were given a list of 5 or 6 covariates, one of which is certainly included precipitation. And I think, precipitation, temperature, elevation, greenness, and a couple of others. The other thing that obviously often is a good predictor is if you've got a proxy for poverty.
Is it easy to get those socioeconomic variables, demographic variables in Africa? Like
It's hard. The other current project, which I haven't spoken about today, is we've been asked to revisit Kenya. We did a study in Kenya recently of ST8, soil transmitted helminth prevalence, using things like elevation of vegetation. And we've been asked to revisit Kenya and see how much better could you have done if you'd had good socioeconomic covariates, because those are more available in Kenya than they are Africa-wide. And the motivation for that, according to the funders, which is Gates, is that if you can demonstrate how valuable socioeconomic covariates are for making local disease predictions, that would stimulate other countries to maybe invest more in those kind of information. It's much harder to get rasters of social variables than it is of physical variables, as I'm sure you know. But in principle, you'd like to have them. And incidentally, again, I don't know what it's like in Spain, but when the REACT team in London who are doing COVID surveys over the last 2 years in England involved Claudio and I to do some geostatistical work for them. Unsurprisingly, if disgracefully, if you think about it, poverty in England is a good predictor of COVID risk.
Yeah, we're basically over time, but perhaps a very last question, comment? Yeah. One or two. This last. Yes.
Yeah, thanks for this interesting talk about this very relevant topic. So I'm wondering if there could be anything to gain from doing, well, at the beginning you mentioned that there is quite a large number of these neglected tropical diseases. Maybe for some you have only very few data, scarce data. So could you maybe gain anything from doing joint modeling of several diseases, like reveal some, I don't know, common drivers, environmental, socioeconomic, or have some transfer of information from disease where you have good data to some where you have, well, not so good data?
Absolutely. And again, you know, as far as the likelihood is concerned, these are just Greek letters, right? So rho and pi could be prevalences of 2 different diseases. The biggest barrier to that is actually the fact that funding agencies are disease focused. Right? So, you know, the work we're doing in Kenya with STH, those people don't talk to anybody about anything other than STH. But the other obvious thing, if you think again about the guy on the motorbike, is to make the field sampling multiplex. The statistical gains might be relatively small, but they're certainly there. But the practical gains of actually doing multiplex field sampling, I would have thought were tremendous, and that really needs some multi-agency coordination that's out with my control. But you're spot on. Yeah.
Okay, thank you.
Good. So yeah, let's thank Peter again, and let's go for coffee.
session with 2 talks and then 2 invited speakers. So we'll start with the first talk, non-parametric test of dependence between a spatial point process and a covariate. And the talk will be given by Jiri Vorak, okay?
Just try talking to this, yeah? Hopefully it's fine. Thank you for holding such a nice workshop. I really enjoy having the possibility to talk about mathematics again to real-life people and not just rectangles on the screen. So the title is the one that I promised to give 2 years ago, and it was part of the project on non-parametric methods for point processes that we worked on with Tomáš Mrkvička, Jorge Mateu, and Jonathan Gonzalez. Over time, the project evolved a little bit, so essentially I will be today talking about this topic, testing dependence between a spatial point process and a covariate, but we add some extra layer, and the layer is removing influence of possible nuisance covariates. It essentially boils down to the problem of selecting which covariates you should include in your analysis. And on this particular part, I mostly cooperate with Tomáš Mrkvička. So the question we are dealing with is if we are able to quantify, somehow measure the dependence between a point process and a covariate, and possibly test whether the dependence is significant. So far, the tools available in the literature cover the tests of independence between a covariate and a point process, both in parametric setting, and to give you at least some references, I provide these 2 papers, but of course many other works have been performed in this direction. And also we have some non-parametric methods for testing the dependence between points and covariates, such as our recent work in this journal. So in our project we developed a couple of new tools. One of those is a correlation coefficient for quantifying, measuring the dependence between the point process and the covariate. And that's a useful tool for comparing different data sets, like saying in this data set the dependence is stronger compared to the other data set. We can get rid of the effect of nuisance covariates in the spirit of partial correlation coefficients. And these 2 tools can be used for quantifying the dependence, and I will not be talking about those today. I will focus on the third part, and that's the testing. Non-parametric testing based on random shifts. Of course, we could use those correlation coefficients or partial correlation coefficients as test statistics in the random shift tests, but they proved not to be very powerful. So I will focus on the test statistic that we have found to be the most successful in solving this issue, and that's something we call covariate weighted residual measure. Okay, to set up the notation, X will be a point process, W will be the observation window, and I distinguish different types of covariates. C will be the one that we are interested in, whether it significantly affects the process or not. And C1 up to Cm will be some other covariates that we want to get rid of, that we admit that may or may not affect the process too, but we want to get rid of their influence and assess the importance or significance of the covariate C. This one. We will assume that all the covariates have numeric values as opposed to categorical covariates, because for those we would need to apply different types of test statistics. So I will focus on numerical covariates. And I assume that the covariates have values available essentially in any location in the observation window, at least on a fine pixel grid as we are used to. The main question is, which covariates should be included in my further analysis? Like, should I include this interesting covariate or should I drop it? I'm sorry. If the covariates are independent, such question is not really difficult, but it's getting much more interesting when we admit that there might be some correlations between the covariates C1 up to Cm with our covariate of interest. Maybe the information that is conveyed by the covariate C is already included in this set of covariates that we want to get rid of. Maybe if we include in our analysis this set of covariates, maybe we can drop this one. So it starts to get really tricky, and this is what we are interested in. If we want to assess if a pair of covariates is correlated, we have developed earlier a non-parametric test for that too. So just a quick overview of Monte Carlo tests, because what I will be talking about will be a Monte Carlo test based on random shifts. We have some test statistic computed from our observed data. In our case, it will be a scalar test statistic. We somehow obtain, say, simulations from a fitted model or some permutations, or in our case, new replications will be obtained by random shifts. And we obtain a set of test statistic values obtained from these replications. And we rank the observed value from our observed data in this whole population of values, and based on whether this T0 is extreme or typical in this population of values, we compute the p-value. The random shift tests are traditionally used for testing a dependence between a pair of spatial objects, and now I'm used to using both of my hands to demonstrate the shifts, so it's tricky for me with the microphone, so I will just be using one hand. So we have one spatial object, like one random field, and another random field. And they have some marginal structure. They might be like autocorrelations inside each of these objects, and there might be some cross-correlation. The two objects might be correlated with each other. So we want to obtain permutations or replications under the null hypothesis of independence, and traditionally we try to obtain those by randomly shifting one of those objects, keeping the marginal structure intact, but breaking the possible dependence between the two objects. Okay. With randomly shifting one of those objects, part of the data moves outside of the observation window. So in case of rectangular observation windows, we can identify the opposing edges of the rectangle and impose the toroidal geometry and make the shifts with respect to this toroidal geometry. And we call this torus correction, and it was suggested already like 40 years ago in this paper. And this requires a rectangular window and brings some liberality to the testing, because the replications obtained by shifting with the torus correction have somewhat different autocorrelation structure than the original data. There is some crack in the autocorrelation structure. It looks like this. Short illustration. If this is a point pattern and I shift all the points simultaneously in this direction by this amount, say this cluster moves to this position, but this cluster is shifted outside of the observation window and it's pushed back inside from the opposing direction. And along these red lines, the autocorrelation structure is changed. These points are now close to this cluster, even though they originally used to be far away. So the autocorrelation structure changes a little bit and then brings liberality to the random shift tests. To avoid the liberality and avoid the requirement of rectangular observation window, in our earlier paper we proposed a kind of different correction. We call it variance correction. And again, I do not want to go into details, just to let you know that yes, now random shifts are available also for irregular windows. And now for the most interesting part. So what turned out to be a successful test statistic for testing dependence between a point process and a covariate. We base our test statistic on residuals as defined in the 2005 paper by Adrian Bedley and his co-workers. In their paper, they defined residual measures based on conditional intensity function, and we will be using a similar version based on intensity function. This was actually suggested by Rasmus Vogel-Petersen in his discussion to this paper. So it's not really our idea, it was already proposed before. So assuming we have a parametric model for intensity function depending on the nuisance covariates, for example, a log linear model is traditionally used. Beta hat will be a vector of estimated regression parameters. Then the residual measure is defined in this way. It's the number of points of the process observed in the region B, and we subtract the kind of expected number of points under the fitted model. So the integral of the predicted intensity function over the same region. So if this intensity function is predicted correctly, this measure should be nearly zero in all regions. Like these two terms should kind of cancel out. Please note that this also covers the case when we do not consider any nuisance covariates and the predicted intensity is just constant. So this case is also covered. An interesting thing to note is that we do not need to rely on parametric models for the intensity function. We can look for estimate of non-parametric estimate of intensity function depending on covariates in some functional form. Now in this form, rho is an unknown function which links the intensity function of the point process with the covariate values at the same location, and the shape of the rho function can be estimated in a non-parametric way by kernel smoothing methods in the space of covariate values, as suggested in another paper by Adrian Bedele from 2012. So based on this idea, we can define fully non-parametric residual measure where the number of points in region B is compared to the non-parametric predicted intensity function. So in the following, I will continue talking about the parametric version, but I wanted to stress that all this stuff can be also done in fully non-parametric setting. Okay, so for the test of independence, the null hypothesis in this case will be that conditional on realizations of the nuisance covariates, so the point process is independent of the covariate of interest. And the test statistic, which we call covariate weighted residual measure of the whole observation window, is defined as the integral of the covariate with respect to the residual measure. And if we plug in what the residual measure is, it's just the sum of covariate values sampled at the points of the process, and we subtract the integral of the covariate multiplied by the predicted intensity. And again, we can do the same thing in the non-parametric setting. Important to note is that for computing this test statistic, we do not need any smoothing. And we do not need to choose any bandwidth. That was not the case for the correlation coefficients that we studied earlier, and that was one of the points of criticism for those correlation coefficients. So in this case, we do not need any smoothing, and if you look at what is the expectation of the first term in these cases, the Campbell theorem tells us that it's just the integral of the covariate multiplied by the true intensity over the observation window. So under, or we can assume, if we imagine that the model is fitted correctly, then the predicted intensity is close to the true intensity, and the expectation of these test statistics would be zero, or the realizations of those test statistics should be close to zero. When we perform the random shift tests based on these test statistics, we obtain a lot of numerical results, and I'm not plotting those now. Just to give you a short summary, the size of the test is correct. Even with the torus correction, the liberality is not very strong, if at all present. So the nominal size of the test is matched correctly, both in the case where the covariate of interest is independent of the nuisance covariates, or in case when they are correlated. And very surprising results were obtained when we studied the power of the tests, because the power was comparable to parametric methods with the correct model. So we essentially cannot do any better than that. And we were very surprised and very happy about the results. And if you would be interested, I can show you a lot of tables to prove that, but I'm not showing you now. To wrap up, I wanted to include this short example about the problem of covariate selection for modeling, because I see our tests as kind of preliminary parts of the analysis, like deciding which covariates should be included in the modeling in the inference, in the upcoming steps of the inference. So I will be showing the traditional Barrow Colorado Island data set with this tree with a complicated name, and I will work with 6 different covariates and perform the random shifts test with almost 1,000 random shifts independently generated in a circle, in a disk with radius 250 meters. And the test will be performed with torus correction and with the parametric residuals. And these are the positions of the trees, and these are the 6 covariates. And we perform the type of backward selection of the covariates. Here I report the p-values. So in the first stage, I include all the 6 covariates to the analysis. And for example, this is the p-value of the test, whether elevation is significant after removing the influence of all the other 5 covariates. And we see a very low p-value. And similarly, for example, this is the number, this is the p-value for the test of significance of acidity after removing the influence of all the remaining 5 covariates. And based on these 6 p-values, I decide that acidity is not important in the model. I drop it, do not consider it anymore. And in the second stage, I perform the test whether elevation is significant after removing the influence of the 4 remaining covariates, and so on. And again, potassium content in the soil was the least significant, so I remove it. And then gradually I remove covariates one by one until at stage 5, the 2 remaining covariates, elevation and phosphorus content in the soil, remain both significant. So my conclusion from this analysis would be, in the future steps of the analysis, I should include the elevation covariate and the phosphorus covariate and drop the others. And that's it. That's everything I wanted to tell you today. Thank you for your attention.
Does not work? Yes. Go.
Have you, given that you want to use this information to carry out modeling, I was wondering, because you're doing variable selection, right? In essence.
Yes.
And if you compare this to regularization type methods, let's say you want to fit a condition intensity model or an intensity model, you could strap on a lasso or elastic net penalty, which would essentially do the same thing, right? And you would, in the case of elastic net, you would adjust for have you seen how your sort of approach compares to that?
Yeah, this is essentially very new work, so we have not compared that yet.
Okay.
And I guess for that you would need parametric models to like shrink the parameters to 0.
All right.
So the main message here is we can do this in fully non-parametric setting, avoiding the model specification. That's my point of view. I would like to push the model specification as far as possible, like make these choices at a later time.
Yeah. Because part of, not concerned, but what I'm thinking there is, if you look historically about how variable selection has been carried out, you started with sort of forward, backward things, etc. And then people, and the PCA and so on, and then people moved on to this joint fitting and variable selection because that was deemed better. But maybe I was just curious if you knew if there was a similar scenario here, but I get your point.
Yeah, thanks.
And one last thing, when you deal with the residuals there, you do have what Adrian and the others called a raw residual, right? You could potentially consider other ones where you have these weight functions in there.
Yes, you could include the weight functions,
Yeah.
work with the Pearson type of residuals or inverse type of residuals. We have not yet tried comparing those because the raw residuals turn out to be extremely successful.
Yeah.
And yeah, this idea is like 2 weeks old, so
Okay.
I still did not have a chance to work with the weighted residuals.
Because the way depending on your weight function, you also change the variance. And that's also again coming back to the what kind of modeling you have. So how much clustering regularity you have. So there might be something to find there.
Yeah, I will definitely look into that in upcoming weeks.
All right, thanks.
Are there any other comments? Quick, because we are a little bit delayed.
So I have a question. How the test you presented work in the case with comparison with a classical parametric method when the model is wrongly chosen? So how we can compare the non-parametric method and the classical parametric method when it's wrongly chosen?
Okay, thank you for the question. That's important to note that I only mentioned the performance or comparison with parametric methods with correct model. Of course, we try to investigate the case when using parametric models with wrongly specified model. And in that case, the parametric methods start to deteriorate, of course, but the non-parametric methods that I presented still keep their power, and they outperform the parametric methods by a great deal. So if anyone is interested in precise numerical results, we have some tables of results in Overleap we can share or have a look at that, but I did not really want to put a lot of tables into the talk.
Thank you, Yeri. I think that it's time to move on. Thank you very much for your talk again. Thank you. So then speaker is Guido Alberti Moreira. So he will be talking about presence only for mark point process under preferential sampling. There is another one here. Hello? Yeah.
Hello. Okay. Cool, I have a green laser. Hello everyone, I'm Guido, in case you didn't know yet. Oh, wait. I'm going to be talking about this topic. I'm working with Raquel Menezes in MU University, and this is a work that's usually applied to ecological problems, but it can be applied elsewhere as well. Let's move on because there's a lot to cover. Okay, I'm going to talk, first I'm going to introduce the problem, then I'm going to talk about what presence only is, then what preferential sampling is. I'm assuming that one or two people in the audience don't know what preferential sampling is. That's why I'm going to talk about it. I'm going to talk about what model we are proposing and some cool stuff about it, what the inference looks like, and what we're doing right now, and then I'm going to talk about where we can move forward. Okay, so this is a simulated data set, which is what we're working with at the moment. Suppose that, well, this is the unit square. Suppose that there is a covariate here represented by this heat map. I'm calling it the sea temperature, the water temperature, and we are applying this at the moment to fish data. More precisely, it's fish data acquired from fishing expeditions. And because there was at one point a very smart biologist who just went into the fishing boat and said, well, we can gather some data from what these guys are catching. So there's information, and we just want to use that information, okay? So here we have a lot of little balls, and some of them are hollow, some of them are full. The hollow ones are just fish occurrences, fish existence, which is not measured. I mean, it's where the fishermen didn't catch fish, either because they didn't go there or because they had to release the fish for some reason or another, or anything else. We also have biomass, means basically the amount of fish that was caught. And the bigger balls are locations with higher biomass, and for those who know point processes can recognize these as marks. So this is why it's a marked point process. And we know that fishermen like to go to where there is a particular amount of biomass. Initially, we thought that fishermen prefer to go where there's more biomass, but then we later found out that nowadays it's the other way around. Fishermen prefer where there's lesser or less biomass. It has something to do with regulatory rules. They can't fish a certain amount, and so they prefer to go where there's less fish, so they don't have to, throw fish away. And so we didn't know this when we prepared this simulated example, so we just put more fishing observations or more fish caught when there's more biomass, because we thought that made more sense at the time. And so you can see that there's a little bit of a sampling problem. Basically, we are only measuring bigger biomasses, so it's a preferential sampling problem, and we're also not measuring, for example, this region here, so these presences are not measured. So we have preferential sampling in the sense of biomass and also in the sense of presences versus absences. Okay, so what was an example of what I was saying, if we were to look at the marks or the biomass only at the observed locations, we would get this smooth histogram, and the red line, the vertical red line here, is just the true mean we use to simulate the data. So we would be overestimating this biomass distribution over the region. And we are interested, of course, in where the fish is located and how much biomass there is in the region for both economical and ecological reasons. Okay, a little bit about presence only. It's basically called, another way of saying it's an opportunistic sampling. When someone observes a certain species, for example, and they observe it not with the intent of measuring absence versus presence. They just, for example, they want to study a certain type of species, and they go and they measure it and record their location, but they only go where it's more accessible, where it's easier, where it's closer to them, so it's a biased sample. In opposition, there's presence-absence, which is basically what you would want, a systematic survey and beautiful sample, which is not what we get. And you can see that fishermen go where they know there's fish, so which is why this would be a case of presence only. Preferential sampling, I'm assuming I only have to speak about it briefly. It just means that we're measuring things that are not independent from how the data is collected. You can think of, for example, measuring air pollution. So you have to spend money to measure pollution, and as you're spending money, you prefer to see where there's more pollution because you want to see the worst case scenario. And if you're supposed to estimate the pollution in the whole region, you would be overestimating it because you only measure the top regions, the top pollution. But also, presence only can be understood as preferential sampling for the reasons I already talked about. So, in summary, the fishermen go where they know there's fish, and they prefer a certain type of biomass in where they fish. All right, so here comes the model. There's a lot to unpack, but let's break it down slowly. This is actually a big Frankenstein's monster of a model because it joins a lot of recent works. You can call it Guido's monster if you want. So first we have the observed locations, which I'm calling X. It's an inhomogeneous Poisson process with a certain rate, a certain intensity function. There's the X prime, which is just basically the locations where the, for example, fish are, but are not observed. And as you can imagine, this is a data augmentation solution. There's this U, which is another Poisson process. I'm going to talk about it in a bit. It doesn't make a lot of sense to talk about it right now, or else I'm going to confuse you if I haven't already. So there's the marks, which in this case, in this example, is the biomass, which is just a gamma distribution because it's positive. And the average is just the log average of this gamma is just a regression model plus a smooth process S plus some nugget. This is pretty standard, right? So okay, here's where the things get a little bit convoluted. I'm just saying that X and X prime, meaning the observed occurrences and the unobserved occurrences, are just their intensity is just the intensity of all the occurrences divided between observed and unobserved. And the observation happens with some probability P, which is intrinsic to every location. For those of you who know point processes, this is thinning. And these occurrences, their intensity, are modeled according to some link function G, which I'm leaving as a mystery for now on purpose, with some regression with covariates, using covariates related to their intensity of the fish occurrences. And as you can imagine, there's a logistic regression to explain the probability of observing each occurrence. But the cool thing is here, this S appears again here, which is the same S as here, and which is basically where the preferential sampling comes in. For those of you who have been up to date with preferential sampling literature, will recognize this as the preferential parameter. And S is just a nearest neighbor Gaussian process for scalability. I'm assuming I don't have to talk about it. Okay, so about this link function, which I left out a minute ago, usually people use the log, as in, since the intensity function is supposed to be positive, then you just use it as the log. And based on some recent research and the paper from my PhD, which was accepted to the Annals of Applied Statistics, which I am very proud of. Thanks. So what changes it is that first we assume that this intensity function is finite at all locations of the region D, and then we rewrite it as a function Q, which is a function between 0 and 1, and a positive parameter lambda star. So if you have the region, you know, the function is supposed to be, okay. Well, I'm going to speed through this because I don't have a lot of time. So it's basically, the idea is this. So I have a positive constant lambda star here, and the process is divided between X, X prime, and the mysterious U, and you superpose X and X prime to get all the occurrences, and you superpose with U just to get a new process which has constant intensity. And what's cool about this is a lot of things. First, for those of you who are familiar with the Poisson process, there's a very unsavory integral, which becomes the integral of a constant in the augmented model. So it's just trivial. So you can actually evaluate the likelihood function exactly. We have smaller identification problems between intensity effects and observability effects. I'm not going to talk about it because of time, but if you want, you can check out our paper in the annals. When we estimate x prime, we actually get prediction. So we get prediction of the positions for free. The marks in the unobserved locations are also need to be estimated, and you also get prediction for them for free. And this data augmentation idea of the x prime and the u is very straightforward in the Bayesian setting, I mean in the MCMC setting. So the Gibbs sampler for them is just another Poisson process, and the sampling of this nearest neighbor Gaussian process is inspired by these smart people here. Okay. For our simulation, which I'm using only an intercept for the marks regression part, and because of a annoying bug in my code, I still have to use S as known, but we're getting there slowly. This is what the development looks like right now, squashing bugs. Our results, I'm going to talk about very briefly. What I'm calling beta is the intensity part, and what I'm calling delta is the observability part, and we are mostly estimating things well. We are overestimating gamma, which was the preferential parameter, a little bit. You know, it was 2, I believe, and we're estimating between 2 and 3. Lambda star is a little bit underestimated, and it has a very high correlation with the number of points in U. As you can see, there is no real value for U because it's completely made up. The number of points which we have not observed is a little bit underestimated, but I think it's because of the underestimation of lambda star. But this is an important part. With this mu here is the mean of the log, wait, 1 minute, of the log mean value for the marks. And we are hitting it on the spot. So that overestimation that would happen if you're not taking preferential sampling into account, you can see that it's not happening here. All right. Where we go from here? A lot of places. First, we finish the bug squashing. We publish the R package to CRAN, possibly with this name, pump, for its presence only for marked point process, so that I can convince biologists to pump their data. I'm going to try to convince the world that fishing can actually get information. Then extensions will include other types of marks, and adding data from other sources, such as systematic sampling, and adding time, because it's important, because fishing seasons change, so it will affect the observations, and you know, fish populations like to act differently depending on time, so this is important as well. Thank you very much.
Lots of things to do for him, right? Thank you very much for the nice presentation. Just time for a quick question, Alan. Just one.
Rather than gammas to model the biomass.
Possibly.
I mean,
But that's not where the hiccup is. This part is actually, it gave me a bit of a headache in the past, but I think I've pushed through it, because the hard part is that you're supposed to be sampling the marks where you've not observed, right? And the very annoying part is that at every MCMC iteration, the points are somewhere new. So you don't have the value in the last iteration to do, for example, a metropolis sampling. But for the gamma example, I've managed to do some transformation, and I can get some independent variables which transformed yield the actual variable. So for the gamma, I'm comfortable at the moment, but maybe I can look at the log normal in the future. Thank you.
Thank you very much, Guido. I think we move on to the next speaker. Thank you. So well, now we have the first invited speaker for this session, which is Ayla Sarkar, and she's going to talk about spatial analysis of epidermal nerves fiber patterns.
Thank you. And thank you for the organizers for arranging this workshop. I think it must have been frustrating not to be able to have it. I think especially for Carlos, who is the local host. So thank you very much for organizing this and having me here as well. So I will talk about this spatial analysis and modeling of epidermal nerve fibers, and there have been a big group of people working on this, and here I will try to say something about the recent work, which is joined with Konstantinos Konstantinou, who is here in the audience and who could as well be standing here presenting, and then Umberto Piccini. They are both at our department in Gothenburg, and then Adam Löwenbrook, who is a neurologist at the University of Minnesota. So I will first try to give some kind of motivation and present the data, and especially what are these epidermal nerve fibers and why is the spatial pattern interesting, and also what happens to these nerves when you get some small fiber neuropathy, because that affects the nerve structure. Then the talk is sort of divided into two parts. So first I will present a point process model for the nerve structure, and then the other part is sort of try to understand what happens when the pattern, a healthy pattern changes and becomes diseased, when the person gets neuropathy. And that is sort of some kind of thinning of a healthy pattern. And then I will summarize. So this is an illustration of the epidermal nerve structure, or what happens and how you can sample them. So here you see the wrong pattern. So this is sort of like the blister roof. So the doctors, they take a skin sample, they pull out a part of your skin, which they call a blister, and then in this blister you see these sort of green stuff, and those are the nerve fibers. So when you, and then as soon as they had it established that, they wanted to know if they have some diagnostic value. And for that they compared people who suffered from diabetic neuropathy, which is one small fiber neuropathy, and they compared them to healthy people. And they saw that the diseased people had less nerve fibers per surface area, and the length of the fibers per volume was smaller, and the patterns were more clustered compared to healthy subjects. And then, since the patterns were more clustered, they thought that, okay, but when you lose your nerves, this doesn't happen completely randomly, but it happens in a way that the pattern is more clustered. And somehow this observation here, so that's why we got involved in the work. So first establish that this is true, that the pattern is more clustered, that it's not only an observation. The data we have skin samples or blisters from both healthy people and people suffering from diabetic neuropathy. And typically we have 2 skin blisters, and altogether we have from 3 to 6 samples per person. And they are taken from foot, And we have 34 healthy subjects, 8 subjects with mild neuropathy, and 5 with moderate neuropathy. We have also some severe cases, but there the number of nerves is so small that it doesn't really make sense to do any spatial analysis. And also now I will mainly concentrate on the, I will mainly concentrate on the healthy and mild group, but sometimes I have included the moderate group in some of the plots. And also we have data from foot, and it's also because we are sort of interested in the early stages of the disease when it's hard to diagnose. So can we see something in the spatial pattern? And the neuropathy usually starts to develop in more distant part of the body, like hands and feet. And that's why we have taken the feet and mainly compared healthy and mild groups. And then how we sort of describe the individual nerve tree. We describe it by using 3 types of points. First of all, we have the base points where the nerves enter the epidermis, and then the nerve starts to grow, and then it branches. And then we look at the first branching point. And now from now on, I will call it only a branching point. And then finally, after several times of branching, the nerves terminate. And those points where they terminate, we call endpoints. And now all these types of points are considered as considered realization from 2-dimensional point processes. And now the data are in 3D, but we are looking at the 2D projection. And the reason for that is that here we look at how the nerves cover the skin. And then that's why the third coordinate is not so important, and the 2D projection is enough. And also another reason is that these endpoints that play an important role, they are the ones that sense heat and pain and so on, and then the nerve fibers send the signal to your brain. And so they play an important role, and according to neurologists, the depth where they are is not so important. It's more the 2D spatial structure. So this is an example of one of the samples. So this is from a healthy person, and you see that the red points here, I hope you are not colorblind. I think the choice of colors is not maybe perfect. The red ones are the base points, and the green ones are the branching points, and then the blue ones are the end points. And as you can see that somehow these look clustered, especially if you look at the end points, the blue points, and you could think that, okay, we can use some cluster processes to model them. The interesting thing here is that we know the cluster centers. So usually we don't know the parent points, but in this case, we know that they origin from these red points, so we know the connections. And then when we model this, we want to take this into account. But this is how we treat the data. And now first we can just look at that, where the neurologist correct when they said that the patterns become more clustered when the disease advances. And one way to look at it is to use some summary statistics, and here we use Ripley's K function. I think most of you are familiar with that. I just quickly recall what it is. So it's defined as the expectation, and this is with respect to the Pound distribution. So you condition on that there is a point of the process in the origin. And then you compute the number of other points of the process within distance R. And then if you divide this by the intensity, the mean number of points per area, you get the K function. Here we use the variance stabilizing and centered version because it's sort of visually very nice. It's equal to 0 if under complete spatial randomness. It's positive under clustering, and negative values indicate inhibition or regularity. And here are the estimated L functions from the data, and now these are all these 3 groups. So these are sort of mean L functions. So first you estimate the L function or the K function for each sample, take a weighted mean, you get the subject-wise estimates, and then you weigh them to get a group-wise estimate. And here you have the endpoints and base points. And now the healthy ones are the blue ones, green ones are mild, and black ones are moderate. And if you look at the endpoints, so they are all clustered since the functions are above 0, except here for base points at small distances there is some kind of inhibition. But here you see that as the disease advances, the endpoint patterns get more clustered. And you can see a similar behavior here at base points, but now the disease patterns seem to be more clustered than the healthy one, but then there is not so big difference between the mild and moderate cases. So we also looked at the coverage, and in an earlier paper we defined a reactive territory of a nerve tree. So, and we defined it so that we take the base point and an end point of one nerve tree, and then plot or drew a convex hull, including all these points. And then the coverage is the area of the union of these convex hulls. And this is what we plotted here, first for healthy group, mild group, and moderate group. So we see that the coverage decreases, which is sort of bad because then you don't sense as well. Then somehow we can get a lot of information from the data by looking at it, but then we thought that we can also model it somehow to try to understand the underlying process that is generating these patterns. And earlier we have constructed models for the base points, for the endpoints given the base points. And now Konstantinos and I thought that we can add information about the branching points. And one reason was that they are more sort of cluster centers compared to base points. So here the dots are the base points, and these crosses here are the branching points, and the pluses are estimated cluster centers, and the triangles are the endpoints. So you see, if you compare where these 3 points are, that the branching point is closer to an estimated cluster center than the base point is. So it's more we thought that it's natural to first model the branching points and then gather the endpoints around that. So what we did, we construct a model for branching points, and given those locations, we then construct an endpoint cluster around them. But all the time we condition on the locations of the base points. And when we construct the model, we try to take into account the hypothesis that the neurologists have. They think that the nerves grow so that the nerve endings cover as much of the skin as possible, so that there would be some kind of interaction between the endpoint clusters. And how we did this, we constructed the branching points, and somehow there were 2 components of the model. First, the distance between the base point and branching point, and then the angle. And for the distance, we used gamma distribution with shape and weight parameters alpha 1 and beta 2. And then for the angle, and now it's angle between if the branching point is sent here, it's the angle between that direction and the x-axis. And here we use the von Mises distribution, which has 2 parameters, mean, angle, and concentration parameter. And now we followed an earlier paper where we were modeling directly the location of endpoints given base points, where we chose the mean direction so that it's away from the nearest other base point. So this is the base point, this is the nearest other base point, so we sent the branching point to the opposite direction. And then this concentration parameter, the higher the concentration, the smaller the variance. So more directed the direction is. And then when we have the branching points, we construct the endpoint cluster, and there we need also the length and the angle, but we also need the number of endpoints per cluster. And the number of endpoints, I think in the very beginning we used Poisson distribution, but that wasn't flexible enough, so we changed it to negative binomial distribution. And now I later show the mean of that distribution, that's why I just put that instead of the 2 parameters. And then again, the branch length is gamma distributed, And here we tried different distribution for the angle, but in fact, uniform distribution was working well. So we took that. And then in this case, parameter estimation is very simple because we assume that the different components, like the number of endpoints and then the lengths, branch lengths and the angles, they are independent. And we can estimate the parameters separately for each component by using maximum likelihood. And then we estimate the parameters for each subject, and there we used all the sample per subject. Here I just show a box plot of the parameter estimates. Of course, you could get similar information from the data, but these are the model-based one, and we checked that these describe the data quite well. But here you can see, if we start, these are the cluster sizes, how many endpoints there are per cluster. And you see that there are slightly more endpoints in the healthy group compared to the mild one. And that makes sense because the number of nerves should decrease. And these are the branch lengths, first between the base point and branching point, and here branching and endpoints. And here also the sort of in the healthy case, the endpoints are further away. And also that makes sense because they are then less clustered and cover more of the skin. And this is the concentration parameter, and now it's 10 times to make it more visual. And the concentration is larger in the mild group, meaning that the direction where the branching point is sent is more concentrated away from the nearest other base point. So then the spatial goodness of it, here we use global envelopes, the rank envelope test, and these are the solid ones are the mean curves, and these are for the endpoints only. So this is for the healthy group, this is for the mild group. And somehow you would like these solid lines to be within the envelopes. They are not completely there, but we thought that it's not too bad, the model. And then we also looked at the subject-wise fits, and they were in fact very good in the mild group and in many of the, for the subject in the healthy group, but not perfect. Okay, so we have constructed models for the endpoints given the branching points, given the base points. But then it's also interesting to know what happens when a pattern becomes diabetic or neuropathic. And we thought that it's some kind of a thinning model, but it's not independent random thinning. Otherwise, the K functions or L functions would have been equal. And then we talked to the neurologist, or especially with Adam, and he said that what they think is that some of the whole nerve trees die first, and then in addition, some of the endpoints may die, or in fact, some of new endpoints may appear. And why these new endpoints appear, that's due to that the existing nerve fibers are branching so that they get more endpoints that can they send to cover the skin better. So our first attempt now was that we are looking at what happens if we just delete some of the nerve trees, meaning we delete the base point together with all the endpoints and branching points connected to that base point. And so we started by constructing patterns similar to the mild patterns from the healthy groups, healthy patterns. And we would like to do it in a way that we get more clustered patterns, both when it comes to base points and endpoints. And here what we did, we took one of the mild patterns, and then we used all the healthy samples to get to that mild pattern by removing nerve trees from the healthy patterns so that we get the same number of nerve trees left that we have in the target mild pattern. And we did this for all the mild patterns. And how we did this, so now here is just some notation. So if you have a base point or healthy base point pattern, and then you can find the nearest other base point for each point in that pattern. And this distance to that nearest other base point is denoted by MYI. So we sort of mark the point pattern by taking the distance to the nearest neighbor. And then this is the retention probability we use, so it's proportional to e to the minus a scaling factor, and here we have the distance to the nearest neighbor. And here this SB, this scaling factor, it's the larger, if it's large, this is almost like an independent random thinning. So the smaller it is, the more the pattern is different from the independent random thinning. And now, when we do this, we remove isolated nerve trees with high probability, and this should result in more clustered patterns. So now, first what we did, so we had this scale parameter that we would like to estimate, and first we just used trial and error, some kind of grid search, and try to find a reasonable value, and we managed, but then we thought that it would be nice to find a way to estimate it. But here we don't really know how to write down the likelihood for this thinning model, and that's why we thought that we could use approximate Bayesian computation, ABC, where you sample from the pseudo-posterior distribution. So here, the posterior distribution is a product of the prior for the scale parameter, and then you are looking at, you choose a summary statistic S, you choose it as you wish, but you would like it to be good. And then you look at the difference between the summary statistic estimated from the simulations, in our case thinnings of the healthy patterns, and compare it to the data-based one, so the summary from the mild pattern. And you want this difference to be small. And typically you fix this tolerance level epsilon, but we decided, so we use rechecks and sampling here. Oh, M is missing. But instead of fixing the epsilon, we in fact simulated a large number of, or did the thinning many, many times. And then we took the parameter values that gave the smallest distance and let that be the sample from the posterior. Then we had to choose the summary statistic. So we wanted to have something that describes the spatial structure. We didn't want to use the K function because we use it then for the goodness of it. So instead we took the empty space function, which is the cumulative distribution function for the distance from an arbitrary point to the nearest point of the point process. So we didn't use the whole function. We took as a summary, we took the distance where this function reaches the value 1/2. So this is sort of a little bit arbitrary way to choose the summary statistic, but it seemed to work quite well. And here we need a prior distribution for the scale parameter, and we just took a uniform prior, and then 0.2 was chosen so that with that value, it's almost like independent random thinning. So we sort of cover the whole range. Here are the posterior distributions, and here this is still ongoing work, so we are not quite sure how we should do that. But what we did here is that now these are all the mild samples, and then they each have an own posterior distribution. And how this is done, it's sort of like it's thinning from healthy patterns which can have different numbers of points. So we are sort of removing different number of points from these healthy patterns to get the mild patterns. And somehow this is one subject, and you see that these three samples, in some sense the SB, the scale parameter, is describing how far from the independent random thinning the sample is. If the value is small, it's far. If the value is big, it's close to independent random thinning. So it seems that these are not independent random thinnings, but the last sample may be. But here, I think we have to work on this more, so these plots may look different in the future. So then we looked at the spatial goodness of fit, and this is again, these are global envelopes based on the posterior predictive distribution, And this is a mean. So here we have again the mean of this comes from mild group now. First for the endpoints and then for the base points. And then the envelopes are constructed in a similar manner that we sample, we take parameter values from the posterior distribution, and then we simulate, and then we sort of like, again, compute a mean from those simulations. And here, if you look at now the solid curves seem to be within the envelopes, so it seems that both the base point structure and the endpoint structure is similar to the data. But here now we have removed only trees. We didn't touch the endpoints. And that's why we wanted to look at some non-spatial summaries as well. So for example, are the reactive territories or the coverage, is it too large if we only remove trees? But now, so we looked at the coverage, and it seems to be pretty nicely fitted with the model. These are again from the posterior and predictive distribution and with global envelopes. And here we looked at the cluster size, the number of endpoints per cluster. And both these sort of non-spatial summaries seem to, or the mild patterns are predicted quite well. So then to summarize, so first of all the models. So now the two-dimensional model that we constructed, we think that it works quite well, but I think it could be further improved. We sort of try to take into account the repulsion between the endpoint clusters. We did it in a very simple way by sending the branching points away from the nearest other nerve. But I think there may be some interaction could be included within the endpoints as well. Then we in fact use this 2D model as a basis for a 3D model, and that is presented in Konstantinos' post. There are also some models for base points. First, we developed a Thomas cluster model. The base points are also clustered, so we use Thomas cluster models to model them, and by using sort of Bayesian hierarchical structure or inference, and by taking into account sort of the hierarchical structure of the data. So there are samples of subjects of a group, and that's why the hierarchical setting seemed to fit well. And then later, Klaus Andersson, who was included in this paper as well, he and Thomas Mritschka, they sort of changed the Thomas cluster model so that they, instead of using Poisson distributed number of daughter points, they changed it to generalized Poisson so that you could have under or over dispersion. So, but what we haven't done yet is to combine these two. We could combine the model for base points with the model for branching and endpoints. And then when it comes to the thinning part, so we only removed trees and didn't touch the endpoint. And now it would be interesting to see what happens if we do the thinning or regrowth of endpoints. Does it improve the model? And then also now I showed only the results going from healthy to mild. We also did a similar approach going from mild to moderate patterns. And there, in fact, it seemed that the independent random thinning is enough. It's sort of reasonable it's enough for base points because there didn't seem to be any difference in the spatial structure, but it worked even when we looked at the structure of the endpoints and the non-spatial statistics. This ABC approach is still under construction, so that may be changing. Thank you.
Thank you, Ayla. Are there any questions or comments?
Hello. Okay. Thank you for your presentation. I just have a very small comment. you were saying that you were trying to modeling the counts with Poisson, and then it did not work well, and you changed for a negative binomial. And I was just asking if you tried, for example, quasi-Poisson or a Tweedy distribution as well, and compare the results.
In fact, our first attempt was Poisson, and that wasn't so good. And then we sort of wanted to have a distribution with 2 parameters, and the Chongai distribution was the one we tried first. And then and we had it, in fact, in the very first paper we had that, but then later on we changed it to negative binomial, which gave very similar results, and only because people know what negative binomial distribution is, but it was often that the people didn't know what the Chongai distribution is. But those 2 distributions that you mentioned, we didn't try.
Any other comments or questions? Okay, go ahead, Radu.
Thank you very much, Ayla, for this very beautiful talk. You just mentioned something about independence of your components. Can you say a little bit? It is a simplifying assumption, it is a medical assumption. So explain a little bit this.
Okay, in the model with it's a simplified assumption. So, yes. I think I can't really say that. Yeah.
We already talked about this, so we'll continue talking. So very interesting. Thank you very much.
You always need to simplify things, otherwise everything is too complicated. Why not to simplify? That's good. Okay, so I think that we can thank again to Ayla and move on a little bit. So the last speaker of this session is again an invited speaker, Bolly, and she will be talking about crop yield prediction using Bayesian spatially varying coefficients models with functional predictors.
Hello. Yes, it works. Okay. I'm the last one in this session, so I will try to be short and not standing in between you and the lunch. This is the last thing I want to do. I'm really excited to be in this conference. This is the first time I attend this conference, this series of conference. And so far, I have enjoyed every perspective of this meeting. Thanks for organizing this conference, and thanks for having me here. I really appreciate it. So I'm going to talk about crop yield prediction using Bayesian spatially varying functional model. Oh, I have this one to use. Okay. First, I wanted to thank my collaborators, Yoonju Park. She's assistant professor at University of Texas at San Antonio. She graduated from our university, and she just started the job a couple years ago. Ye Hua is a professor at University of California at Riverside. He was my graduate kind of a classmate when I was a student. So agriculture is a very big thing in the United States. I just wanted to throw some numbers to show that how much GDP agriculture has contributed to the US economy, and also how many job opportunities the agriculture provided. Just in 2019, it provided 11% of the job opportunities. Midwest is one of the world's largest crop production area. Midwest in the United States includes, I forgot, maybe 8 or 9 states. Many of the Midwest states is on the very famous corn belt that produce lots of corns and soybeans. So just the Midwest, it produces 85% of US corn and soybean. So I live in Midwest, so I know this because from my house, the left side is cornfield and the right side is cornfield too. So I can see lots of cropland there. It's very important to have timely and accurate yield prediction because the policymakers wanted to know this information to deal with the potential food crisis, and also it's important to plan for storage, distribution, and also trading for agricultural products. So how should we make a prediction of a crop yield? Studies have shown that weather data, like temperature and precipitation, has a very significant impact on the stages of crop yield growth, and then because of that, it affects agricultural productivity quite significantly. So there was a paper showing that 60% of corn yield variability and 36% of soybean variability in the Midwest area is explained, I wouldn't say caused, is explained by climate variability. So because people have recognized the relationship between crop yield and weather variables for a long time, so different approaches have been developed to try to use that information to make a prediction. And some are, let's say, from the crop scientists. The first one, like some. So some are like simulations, like just to simulate the crop yield growth process, and try to use that to make a prediction of crop yield. And then for another set of papers, they try to use some like a simple statistical approach, like linear regression models, to connect the crop yield and the weather data. And nowadays, machine learning methods have been used everywhere, and also in crop yield, there are like different machine learning methods such as neural network models, and also XGBoost methods have been very popular for crop yield prediction. In a very recent paper is using functional regression models. They treat the temperature data as a functional predictor rather than just use some summaries of temperatures, let's say some mean temperature or some degree days, which means the number of days the temperature is above a threshold. So those are some of the previous work. And also in the previous literature, and it's found that the maxima and the mean temperatures particularly are important and affect crop yield at different stages. So this affection is not like a cumulative effects, like average temperature or something, but it affects the growth of a crop on a daily basis. So because of that, then it's very natural to treat the trajectories of temperature as a functional covariates. So it would describe the relationship, and how not just the relationship, it will describe how the temperatures affect crop yield, crop growth on a daily basis, not like just use the, as I mentioned, just use the average temperature, and then you will miss lots of details for that. When we use the functional regression models, and I wanted to give a little background of functional regression models. So there are many different functional regression models. You can have functional data on the left-hand side, like the y variable, and then you can also have functional data on the right, the x variable, or you can have on both sides. And then there are like early on, there are some functional linear models, and so this just like describe linear relationship between the functional variable, functional covariate, and the y variable. And then later, the additive models try to describe a non-parametric relationship between the functional covariate and the y. In the partial linear functional additive model, so you have additive component of functional covariate, and then you have some linear component of the covariate. And the functional additive mixed model, this has been used widely for longitudinal data and the repeat measurement to just describe the group effects of your data. So that's where the mixed come from. So there are a lot more literature. So I think many people in this room, like Jorge, worked on functional data. I hope I didn't, maybe I missed some literatures from you, and I'll catch up with you later. And for those literatures that I just mentioned, that they often treat the functional covariate as independent. But for agriculture data, let's say you observe the temperature data on a spatial domain, so they're likely dependence between the functional covariates. Let's say there must be, so if the two locations are close by, and then we would expect there is dependence between the temperature trajectories at those locations. So I think this component is important, or is a special feature for spatial functional data. And another one is if you observe your data at the large spatial domain, and then it's not very realistic to assume that your y variable and your functional predictors have followed the same relationship. So for agriculture data, let's say, other than the meteorological, other than the temperature weather data, there are some like soil conditions and soil moisture that can affect the relationship. So very likely you would have different relationships, have different locations. And because of those reasons, and we propose this Bayesian spatially varying functional model for crop yield prediction. And this one is based on the idea of Alan's paper. Actually, I have used this idea on several of my papers. I found it's really useful to describe the spatial data, the characteristics, to characterize the relationships between data observed on a spatial domain. So in our model, we mainly did the three following things. So one is taking into account the spatial correlation of the functional covariate, and also we also were taking into account the measurement errors. We allow the spatially varying relationship between crop yield and the weather data. And then we also incorporate a Bayesian variable selection to further respect the heterogeneity of the relationship between crop yield and covariate. So I will talk more details on this next. So first, I wanted to introduce what the data we are focusing on. We have the crop data, which is a corn yield, average corn yield, and is a county level data. So we look at 5 states, the 3 famous I states, Illinois, Indiana, and Iowa, and also Kansas and Missouri. Those 5 states are all Midwest states. And it's annual data for 22 years between 1999 and 2020. So there are 542 counties, but we found that 403 has data with more than 5 years. So because for the counties that have less than 5-year data, we'll just discard that because we think those are probably the counties that do not have cropland, or at least is not important for the corn yield. And here I just wanted to show some examples of the maxima and the mean temperatures in 2 states. One is in Iowa, and the other one is in Kansas. So those come from randomly chosen counties in 2 states. So you can see that even the states are close by, but the temperature characteristics are still different. So our predictors in our model would be the daily maxima and minimal temperature, and also annual precipitation, because it has been shown that how the precipitation affects the crop yield is in a more cumulative way. So the annual precipitation seems like is a pretty good predictor for that compared to the temperature data. So although we like the spatially varying, like a heterogeneous data, but we don't want to propose a model just because this is flexible. We want to first explore the data and see if the data ask for that. So after we have the data, we first did a preliminary data analysis. And in our analysis at each county, we first do some like a very simple regression model. And with the function, so at each county, we first find the functional PCA of the temperature data, and then we use the first two leading FPCs, and then use that to fit a very simple linear regression model with the Y as crop yield, and this is the coefficients for the first PC, and this is a coefficient for the second PC. So you can see that the coefficient actually are quite varying over counties. So and even the sign could be different. And the same story for the second PC coefficient. They are quite different over different regions. But we also observe that they are clustered, so the errors, so the residues from their model. And then I found that the residues actually, for some states is always positive, some states is always negative. And then I feel there's lots of local bias if you just use one single model for every counties and states. Okay. So now wanted to define our method, define our model. So first we wanted to have define some notations. We use Y to denote the average corn yield. And S is the spatial location. And X is a vector of functional predictors. And here S is still spatial location, but T now is index in the functional space. And the Z is, we can have a multiple scalar predictors. So particularly for our crop yield data that I just mentioned, we only have two functional predictors, which is the maxima and the mean minimum temperature trajectories. And we only have one scalar predictor, which is annual precipitation. So now we propose this spatially varying functional model. So this is the intercept, and then this is Z is precipitation. So we just have a very regular scalar covariate here. And then here X is a functional covariate, and eta is a functional coefficient for this covariate. And because we already use a spatially varying coefficient for the alpha and for the eta, so we choose the residues to be IID to avoid identifiability issue. And then, so for functional regression, the first thing we wanted to do is to reduce the dimension, because your functional data has infinite dimension, and we wanted to find a low dimension representation of our bivariate functional predictor. This is we just follow the tradition to project our functional predictor onto a finite number of basis function. So here X is our bivariate functional predictor, and mu is the mean. And then we write the residues into a linear combination of a basis function. Alpha is basis function, C, this is the coefficient. And again, we basically write this for each location S, but later we will try to regulate this to make the X is spatially smooth, continuous functional predictor. And then, in the similar way, we can project the functional coefficients in front of x, also project them into the same basis function. And then we also require the basis function to be orthonormal basis. So if you require this orthonormal basis, and then if you plug in this one to this model, if you plug in x and eta into this one, and then we can easily write this linear regression into a lower dimension. So now you have C, this is like the FPC scores, and then beta is a coefficient for those PC scores. So now basically C is your covariate and Z is your covariate. And so you reduce the dimension. So here we also wanted to consider the measurement error. This is because for temperature data, especially for the local temperature data, it's very well known that they are very noisy. And so we wanted to take that into consideration. So we take the most common additive measurement error models. So our observation, suppose our observation is W, but we do not observe this x functional covariates. Instead, we just observe x plus this additive errors. And this additive errors is again white noise error. And then after that, we can also write W into the low dimension projection onto this a few basis functions. And so I just talk about how to reduce the dimension of functional covariate. And the last thing I wanted to mention is, so usually when people do the functional, if you use frequentist method to do the functional regression methods, you will just use the empirical covariance of functional covariate and then find the functional PCs and use that. But here we will do fit the model using Bayesian, in the Bayesian framework. And we also do not want to directly use the empirical functional PCs because that would underestimate the uncertainty from this part. So we will estimate the basis function, the f function, and we follow a paper by Cowell. So the functional basis function would again be written into kind of a combination of a known basis function. So the phi is a spline basis function, let's say, and then the d is unknown covariate, unknown coefficients for that. So I also mentioned that we want to do a spatial variable selection. The reason is because usually, when you use the functional covariate, you will just use the first, let's say I want to use the first 5 leading functional PCs or first leading 10 functional PCs based on how much variation those first 5 or 10 leading PCs would explain the variability in the X variable. But for a large spatial domain, so some counties, they may find that the first 2 PCs are most useful, but for the other county, they may find that the first and the 5th PCs are most useful. So because of that, we want to make it more flexible. And we introduce a binary indicator variable, gamma. And so if gamma is 0, and then we do not select beta is 0, means we do not select this functional PC. And if gamma is 1, then we do select that PC and then estimate what beta is. We introduced, but also for the gamma, this binary variable, it should be also spatially smoothing process. And because of that, we introduced a latent process new. And in this, the latent process would be a spatially correlated process. So by doing that, we preserve the spatial continuity of the gamma, of the binary gamma variable. And then after that, and then we further can further write our model into a similar thing, but now you replace beta by beta times gamma. So if gamma is 0, then this part will disappear, and this functional PC will not be included or selected into your model. We also learned from Alan's paper that if you use this spatially varying coefficient model, and you need to put some regularization on those spatially varying coefficients, otherwise you would have overfitting, very serious overfitting problem. And so for some data, actually you probably cannot even estimate the parameter without regularization. So we would use use a Gaussian correlated process to regularize all the coefficients, beta and alpha, c, and also the latent process nu. The latent process nu. So, for example, we can just use a Gaussian process with a covariance model as variance times correlation function. So here there is a for the correlation function, so usually for aggregated, this is a definitely aggregated data because it's county level data. And usually you use like conditional autoregression model, this type of thing, to describe the correlation between aggregated data. But here we think a geostatistical covariance model is more appropriate because the correlation mainly comes from how close, how physically close the two counties are. And then because they are close and then their weather conditions, their soil conditions are the similar. It's not like for the epidemiology data. If you share borders, the two counties share borders, and then you think that the data are more correlated. So I think it's a different mechanism behind that. So I would prefer to use a geostatistical covariance model for the role for the covariance function. So I have just mentioned all the pieces of the model and measurement errors. And then in the process, in this level, we just put all the regularization of all the unknown coefficients to follow a Gaussian correlated Gaussian process. And so those are some details for the data. I'm not going to go through all the details, but I wanted to mention that. So to do the variable selection, we also need to focus on how many functional PCs, and this P determines this P is the notation for how many functional PCs we would consider in our model, and we use the DIC, the Devens information criterion to choose the P, the parameter P. And then after we feed the model, so we just I described the model, and then the next thing is to just simultaneously estimate the model parameters and perform variable selection and make a prediction, all of them together. So there are different strategies, I think, to make a prediction. Sometimes you first feed the model and then you make a prediction, or you treat the unknown variable as as parameters, and then you do them simultaneously. We choose the second one, and then after we feed the model, we get the posterior estimate. We get the posterior samples. We will just use the posterior mean and the quantiles to be our prediction, and also the credible interval for the prediction. So how much time I have? 5 minutes, so okay, great. I will skip the simulation, most of the detail. So just want to show that we compared our model. This is the Bayesian spatially varying factor model. This is our model, and then we compare to other functional regression models, but do not have the spatially varying coefficient. And so we consider 3 scenarios with different strength of correlation. The the low correlation, the moderate, and the strong correlation. So we can see that the mean square, the y is a mean square prediction error. So our model works better than other 3 functional regression models that do not have the spatially varying coefficient. This is to show the residues. And so first, like using spatially varying coefficient, we can see we captured more variability. So we have smaller residues, but more importantly, I think it just like breaks some clusters. So you can see there are some clustered residue in the other models, but this one clearly that do not show clear cluster pattern. And then now, just wanted to come back to the crop yield data prediction that for the data I described. So a quick recap of the notation: Y is the corn yield, and the Z is precipitation, and the W is the temperature trajectories. So those are some details how we fit the model. So one thing I want to mention is to make the model more parsimonious, we choose we assume a common range parameter for all the alpha, beta, Xi, like those. So this apparently, this of course make the model have much fewer parameters, but we don't think it's very unreasonable because all the correlation comes from the same data set. And so if they use the same data set, and then correlation strength are probably similar. So we think this is a reasonable assumption. So we use the DIC, and the DIC choose p equal 5. So we will consider five functional PCs. And in order to evaluate or compare our prediction results with other methods, we use 2 types of mean square prediction error. One is a regular mean square prediction error. The other one is a weighted mean square prediction error. The reason we use weighted with this W is the size of harvest land, is because some county has a larger crop land, and some county has fewer. So definitely the county with a larger crop land probably weight more when we evaluate the prediction results. So this shows our prediction results and several models. This is a partial linear functional additive model. This is the functional generalized additive model. This is a functional linear model. And we also compare to 2 machine learning methods, the neural network and the XGBoost. So in all those methods, we found that we achieved the lowest mean square prediction error, and even compared to the 2 machine learning methods. So the XGBoost, this is a very, I think this seems like works well for many data sets, and it's a winner for the Kaggle platform. And it does appear to be the second best model. But for both methods, we found that it's difficult to choose a tuning parameter. So we have to spend a lot of time to choose a tuning parameter to give a better results. And so this is an example just to show our prediction and the true crop yield. So the black is the true crop yield, and the red is our prediction. And we also give the confidence intervals. Different length of confidence interval is because the cropland size is different. So the variability of different county, the variability of data aggregated at different county is different. And then we also show, I want to show some results. This is the alpha, the coefficient in front of precipitation. And those are the coefficients for the first PC, second PC, and the third PC. So the yellow dots are the counties that you choose this PC in your model. So if there is no yellow dot, then that means for this county, this PC is not selected for this county. So we do see that actually the coefficients are very spatially varying as we conjectured. So to further appreciate the benefit of having spatially varying coefficient, and we just try to show the results. Let's see, the purple one is our final result. The result with our model and with a spatially invariant functional regression model. So you can see that this column is for Illinois, and this column is for Iowa. So both. This top row is the purple is from our model, and the purple from this row is from the spatially invariant model. So you can see that spatially varying coefficient model capture a lot more variability compared to the other one. And this is the posterior probability of how you select the first PC and the second PC. So this the color represents the probability of selecting the first and the second PC for different counties in the 2 states. So I wanted to quickly summarize what I just talked about. We developed a Bayesian spatially varying functional model to predict the corn yield. We treat the maxima and the minimum daily temperature trajectories as spatially dependent functional predictors with measurement error. And we use annual precipitation as a scalar predictor. We allow for different response predictor relationship for different counties. And we also did a spatially heterogeneous variable selection. And we did find that our model outperforms other spatially invariant model and some machine learning methods in both simulation and also real data analysis. So one thing that we think is for the soil properties and irrigation, those probably will be very important for the crop yield, to describe the crop yield variability. But we searched for the public, we searched on the internet, we just couldn't find such data, publicly available data. So that's why we didn't use it. But in the future, I think if we have such data, we should try to use it to further improve the model. Okay, thank you very much.
Okay, I think that we have time for a couple of questions at least. Are there any comments or?
Yeah, Alan.
Bo, I mean, the model is really rich, and it looks like you've labored over a long time. I just have some naive question here. It seems like crop yield is an aerial measurement, and you're envisioning a point level specification for it. There's no such thing as a crop yield at a point, so did I miss something about why you're working with sort of point referenced specifications?
Oh, yeah, I think the crop yield data was come out as the county aggregated data. We didn't aggregate that. Is this your question? Do I understand it?
Well, no, the actual Ys that you're analyzing are at aerial scales?
Yeah, aerial scale.
That's all I'm saying, but the modeling is at point level.
Point level.
Well, are you using the centroids of the aerial units to calculate to specify the correlation structure?
Yes.
Okay, so all I'm saying is it's kind of a discrete spatial model being modeled by continuous spatial.
Oh, you mean like why we use a continuous model to model this aerial aggregated data? This is a great question. So we could use like aerial aggregated model. Kind of like so I think mainly what effects is how you model the correlation structure in this model, right? So whether
you want to model sigma rather than sigma inverse.
Model sigma and
usually you model sigma inverse with aerial data. Right?
Oh yes.
But here you want to model sigma.
Yeah. So here I thought the correlation structure mainly kind of should follow should follow a geostatistical covariance model, because I think for public health data, epidemiology data, you often think if the area has shared borders, and then they are more correlated. So most of the covariance models, they use whether the area share borders or not. But here, I think it's because the correlation comes from how physically close the two counties are, not because they share borders or not, because the soil and the weather mainly affects the crop growth. So that was, I know we do see some other papers also use the geostatistical covariance to model the crop yield data. Yeah. Hope this answers your question. Yeah.
Another comment.
Yeah, thanks for the very clear talk and the rich model. And I was curious if you could comment about the computational complexity of your model compared to the others that you tried, like the machine learning model.
Oh yeah, that's a great question. Right, yeah, our model, the computation, I forgot how long it takes. Okay, of course, Yungju, my collaborator, did all the computation. I didn't do, so I don't. She mentioned that to me. I forgot. So yes, it takes more time than neural network and the XGBoost. But the neural network and XGBoost, we have to use different tuning parameters to try to explore. But if you just look at one to generate one result, and like a one run to get the result, and then our method is much slower than the machine learning methods.
Could you quantify much?
Oh, I can tell you later because I really don't have that in my mind.
Sure.
Yeah.
Thanks.
Thank you.
Yes, Peter.
It's really going back to Alan's question, but a different slant on that is I think it's an unfortunate historical accident that spatially discrete models are conventionally specified in terms of contiguities between areas. Mm-hmm. But actually, for the kind of geometry that you've got in those US counties, it's probably pretty good. But I think it's often misused when you've got a very irregular geometry. So I don't think there's any good scientific reason for it, but empirically it kind of works because it's a parsimonious assumption. And I mean, there's a very little known obscure paper by Julian Bizag, which goes right back to 1975, I think, in a journal that no longer exists. But he characteristically said, you can do this, but be very careful, because it doesn't always make sense. And yet, everybody's forgotten that. And every cancer atlas I've ever seen just uses it uncritically. And I do think it needs a lot more thought. But actually, I think for the kind of geometry you're dealing with, I think the usual specification of Markov random field dependence probably makes a lot of sense.
Oh, okay. So do you know the paper? I can probably later email you. So you said the journal doesn't exist. Okay. Yeah, thank you for the comment.
Another one question. My question. You did cross-validation here, right? But you have dependent data. How you do that? How you choose the test set, for example?
Oh, we simulate the data. So in our simulation, we try to make our data look as similar as the real data as possible. So we use basically the geographic data as our test set, randomly choose 20% and 80% as training data set.
But you did this randomly, but you have spatial correlation here, right? So.
Oh, okay.
So I'm not sure if the procedure is designed for spatially correlated data, no?
Oh yeah, so 80% of the data as we did just randomly choose. We didn't consider a block, like let's say randomly choose a block or something. Right. Okay. Yeah, that's a great point.
Any other comments, or perhaps it's time? Yes. Okay, Paula.
Thank you for your presentation. So I was thinking that crop yield may also be affected by temperature in the past. So I don't know if it would be easy to extend the basis to take into account the light effects as well.
Oh,
of the covariates.
Yeah. So this year's crop yield may be affected by previous year's temperature. Yeah, that's I think that's very reasonable. Yeah, excellent point. Yeah, we could extend our model to, yeah, we could.
But
yeah.
the basis now would be three-dimensional, or the basis you construct for the splines?
Currently, we didn't make the past temperature into our model. We just use the current year's temperature. But I think you raised a very good point. I think probably for past years, maybe can use just average past year temperature as a covariate into the model.
Yeah, but I was thinking not only including previous times of the covariates as a separate covariates, but putting them, all of them correlated. So space, delay effects, and effect of covariates, everything correlated, like sharing information. So not considering delay effects, so time -1 independent of time -2.
So I wanted to clarify that for our model, currently for our model, we did not consider the temporal correlation. We only consider the spatial correlation.
Yes.
And so what you are suggesting is to put like past year's data and then also consider the temporal correlation.
Yes.
Is that right?
Yes.
Yeah. Yeah, I think that's an excellent point. And even the previous year's crop yield probably also can be an indicator for the next year's. Yeah, that's a great point. I think it's very worth to explore this.
Thank you.
Thank you.
I think that we can finish because it's a bit late. Thanks, Bolly, again. And there will be an announcement by Carles.
Hi, now it's lunchtime. The lunch is downstairs. And then for those of you who has ordered a vegetarian dish, just order the waiters. And then the evening session, it will start at 3 o'clock here. Okay. This is for tomorrow.
Thank you.